Hey everyone, these are the graphing problems from our Unit 3 review. I had some requests on these, so I'll just kind of talk through a few of them and how we want to approach these problems. So I'm going to start with 18. This is on the second page of your review. The note I have here, we want to just, when we're graphing an exponential function, plugging in values for x is really just the name of the game here. I want to urge you guys to use values for x that make life easy on you. What do I mean by that? Well, if I have an exponent of 0 or 1, that's going to be pretty easy for me. So I'm going to let 2 be one of the values I'll plug in, as well as 3. I'm leaving some space above and below to just make sure I don't have any other points if I want to plot more points, I have some options on where they can go. So when I plug in 2 for x, I get 0 as an exponent. So it's really 2 times 1. So our point 2, 2 is on the graph. If I plug in 3 for x, my exponent is 1. So I really have 2 times 1/3 or 2/3. Just to help make sense of things, I'm going to go ahead and plot those points now. 2, 2. And 3 2/3. I can see that this is a graph that will shrink from left to right. So I'm just going to verify that. I'm going to plug in 1 as an exponent. Excuse me. And when we get that, we really have 2 times 1/3 to the negative 1. Well, 1/3 to the negative 1 is really 3. So that gets us a point of 6. So the point 1, 6, 3, 4, 5, 6. This is also on our graph, and I think at this point we have enough information to say that we know what our graph looks like. I'm going to go ahead and extend this upward and then curve my graph through the points that I found. This is an exponential function, so it has a horizontal asymptote. And that horizontal asymptote here is at y equals 0. Our domain for any exponential is going to be infinite. And our range will be based on the asymptote. In this case, our asymptote is at 0, and our graph moves up from there, so our range goes from 0 to infinity. So we're going to keep this going here. I'm going to move over to number 19. And on this problem, we have e to the negative x minus 4. So again, I'm going to start from a table, and again, I'm going to plug in values that just make my life a little bit easier, numbers that are nice and easy to plug in. 0 will be a good one. In this case, negative 1 will be a positive one to use. And let's just use regular old 1. Let's see what happens. When I plug in negative 1, I end up with e to the first power. That's about 2.78 minus 4. We're going to use approximation here, but what we'll end up with is about negative 1.22. Understanding that when it comes to graphs, being exact isn't quite as critical as if we're solving an equation, right? Because there's always some amount of approximation happening. If I were to raise e to the 0 power, I'd have 1 minus 3. So I'd get 3 there. And if I were to plug in 1 as an exponent, I would get e to the negative first. So I'd have 1 over e minus 4. 1 over e is, oh, sorry, I think I made a mistake there. It's going to be negative 3 for y. Apologies. When I plug in 1, I get 1 over e minus 4. 1 over e, I'm approximating to be about 1/3. If I subtract from there, I'm going to end up approximately at negative 3 let's say 7. Not perfect. I'm doing this without a calculator. My expectation is that when we graph, we're doing most of it without a calculator. So this approximation can be necessary. So let's plot the points we know. Negative 1, negative 1.2. That's right about there. 0, negative 3. And then positive 1, negative 3.7. This graph is going to look pretty similar to our last one. With this shift down 4 units, that is our horizontal asymptote. That's going to be at y equals negative 4. Then I'm just going to connect my points shaped to the asymptote, and then over to the left, it will grow in that direction. Let's finish up here. We have a horizontal asymptote at y equals -4. Our domain is -infinity to infinity, and our range is -4 to infinity. Big idea with exponential models is we want to, we want to plug in values that make the exponents easy to work with. We really want to lean on our understanding of exponentials because that's really what we do with logs. We really graph the inverse of exponentials rather than worrying too much about logs. So just investigating here, I have a log, the natural log of x minus 3 plus 2. So this is going to be our natural log of x shifted right 3 and up 2. So what I want to do is I want to rewrite this equation here. Y equals the natural log of x. I'm going to write that in exponential form. That's going to be e to the y equals x. So remember, we're still transforming this function, right? These transformations will still matter. So what I'm actually going to do is I'm going to start with a table of e to the y equals x, and then I'm going to transform that table with our shifts right and up. With logarithms, my recommendation is to convert to exponential form and plug in y as your input as opposed to x. What do I mean by that? Well, we can choose any values we like. Let's say -2, -1, 0, 1, and 2. We don't need that many points, but I think it'll be helpful to determine which ones are useful and which ones maybe not as much. Well, if I were to plug in -2 for y, x would be 1 over e squared. If I plugged in -1, I would have 1 over e. If I plugged in 0, I'd have e. If I plugged in 1, if I plugged in 0, I'd have 1. If I plugged in 1, I'd get e. And if I plugged in 2, I'd get e squared. That's not our function. I'll have to transform it. This function still needs to go right 3, and it needs to go up 2. So our new and improved, the function we're going to graph here, we're going to add 3 to our x. So e squared plus 3. 1, so that's 1 over e squared plus 3. Sorry, I'm getting a little crowded in here. Let me zoom in a little bit. Let's see, everything. So our next entry is 1 over e plus 3, 1 plus 3, e plus 3, and e squared plus 3. Those are going to be the x values that we actually plot. We'll try to pick out a few that are relatively easy to approximate. Our y values are going to be easier to work with here. We're just adding 2 to them because our graph is shifting up 2. Adding 2 is going to be a little bit easier. We'll end up with these 0, 1, 2, 3, and 4. So this new graph, this new transformed function is what I'm going to apply to my graph. I'm going to pick and choose. I want to choose points that are relatively easy to plot. And I see one there, 4, 2. 1, 2, 3, 4, up 2. 4, 2 is a nice, easy point that we can plot here. This graph will gradually increase as we go to the right. So I think I want to kind of bend back and see what happens as we get closer and closer to x equaling 3. So if I plug in, let's say when y is 1, that happens as 1 over e plus 3. 1 over e, about 1/3. This is going to be about 3 and 1/3, comma 1. 1, 2, 3, and a little bit. There's our next point. If we go 1 point to the right of 2, e plus 3 is about 5.78. So here we go, 1, 2, 3, 4, 5, and, oh, that's too low. It's gonna go up 1. And now you can see with 3 points, we have enough to give our graph some shape. This graph will go down straight just about along our vertical asymptote, which occurs at x equals 3. The last piece is here. I need to figure out my domain and range. My domain is starts at 3, not including 3, and continues off to infinity. Our range is infinite. Our range here will go from negative infinity to infinity. So what did we do here? We really we plotted, I found the points for the related logarithmic equation in exponential form. I got rid of my transformations to start, and then once I found basically our parent function, I applied those transformations moving right and up to create my new table of values. Let's do that one more time on number 21 and see how it goes. So in this case, the related equation is y equals log base 5 of x, and eventually that's going to get shifted left 6 units. So the reason I want to write this in the non-transformation form is because I don't really like logarithmic form. I'd rather write this in exponential and then plug in for y values. This one should be a little bit easier. So I'm going to plug in y values of, let's say, -2, -1, 0, 1, and 2. Again, I'm just casting a wide net here. I don't know exactly where I'm going to end up, but those middle 5 values, -2 to +2, are relatively easy to evaluate. If I plugged in 0, I would get 1. If I plugged in 1, I'd get 5. 2, I'd get 25. The pattern as we move down our table is we multiply by 5. And as we move up, we divide by 5. This is not our function that we want. This is our related function that we will have to transform. So what we need to do if we want to move this left is we are going to subtract 6 from our x values. So 0.04 minus 6, 0.2 minus 6, 1 minus 6, 5 minus 6, and 25 minus 6. Our y values are unchanged. Let me make sure those are labeled. Our y values are unchanged, so we can just borrow them from our parent function table, and we have what we need. So we have a vertical asymptote at -6. 1, 2, 3. 1, 2, 3. So I'm going to sketch that in here. First one didn't go great. So there's my vertical asymptote. Now I'm going to plot my remaining points, making sure that I'm using the correct table. 0.04 minus 6 is extremely close to -6, and the y coordinate is -2. We are somewhere right around here. 0.2 minus 6, again, very close to our asymptote, just one notch higher on the y coordinate. Then we get -5, 0. That's going to be our x-intercept. We also have -1, +1. And I don't think that 19.2 is going to fit on our graph, but we have plenty. I'm going to fit this curve. This will behave asymptotically in the vertical direction and then extend to the right. We have a vertical asymptote here at x equals -6. We have a domain from -6 to infinity, excluding -6, and a range that is infinite. So just to wrap things up here, when I find exponentials much easier to work with than logarithms, so much so that the work we do in exponentials can be carried over to the work we do with logarithms. I want to use the fact that exponentials and logarithms are inverses of one another. That allows me to plug in values for an exponent for y that makes the calculations much simpler. We will have to apply transformations occasionally, but that shouldn't throw us off. Please feel free to reach out with any additional questions.